Então,
good afternoon to everyone. I was asked to perform the presentation in English.
he was also, I just would like to so the first presentation will be performed by Professor Miguel Abreu Almeida Mendes. He is Assistant Professor at Instituto Superior Técnico, integrated member of IDMEC. He leads the Combustion Laboratory at IDMEC IST, and he has been involved in several projects in applied thermofluid dynamics, has been co-authorship more than 40 scientific articles published in the Renowned journals, and today he is here to present to us the eliminating fossil fuels in combustion-based systems. Many thanks, and
thank you very much for the introduction. Thank you very much for the invitation, and it is a pleasure for me to be here, and I'm jealous that you have the university in such nice place, with such nice atmosphere, and I hope that I can bring, let's say, some useful information to you. Okay? So, actually, eliminating fossil fuels in combustion-based systems, the question is the transition to what? Okay, so this is the main, let's say, objective of this presentation, to transmit here the actual situation. So before, let me just make a short introduction. As it was said, now I took very big responsibility of coordinating combustion laboratory of IDMEC IST that was led by Professor Mário Costa, and actually he created this laboratory, and he was a person that was known, let's say, worldwide in the field of combustion, particularly industrial combustion, okay, not just fundamental studies but applications. And at the moment, okay, we have not so big team. Actually, I want to highlight, we have one PhD from UBI that is staying there, although he's doing the PhD here. We have collaboration with Professor André Silva, and so this is just to give you perspective that we have an open laboratory. So if you need to do something or you need something, just send us an email, as long as we are able to give you support. So our research areas, you have them here. More or less, we are focused on biomass thermochemical conversion process, so like carbonization and other processes without oxygen. So here we don't really have combustion, is pyrolysis, let's say. And then some research in alternative fuels to the conventional fuels, fossil fuels, so hydrogen, ammonia, sometimes multi-fuel systems, and particular applications. So this is where we have cooperation with UBI and ZAP, so sustainable aviation fuels. And then other, let's say, side activities, basically trying to relate chemical energy storage in form of fuel with solar energy, solar thermal energy. So small scale, low cost technology transfer. This is something that is useful, for example, for developing countries. So industry is not very interested in this type of projects, but thermal solar coupling, particularly when you have endothermic process, this may be interesting. Solar concentration, high temperature, and then the skills that we have in our team. So from experimental design, testing of reactors, and also some numerics, and also some assessment methods like technical economic analysis or life cycle analysis. So, okay, let's go directly to the topic. So, available energy for combustion. So the first thing we need to understand with all this transition that we are facing nowadays is that all energy sources are from a renewable origin, even fossil fuels. The main problem here is the formation time scale. Okay, so what we call a fossil fuel, if the formation time scale is much larger than the human scale, let's say the scale of utilization. And the renewables are now, let's say, the focus, basically because there are some issues at the moment in terms of sustainability. But keep in mind that in the end, all the energy sources are renewable. And at the moment, the main problem, according to data we are facing, is the CO2 problem. Okay? But we are still relying on fossil fuels in a very strong manner. So we cannot just turn off the lights and stop the car. Okay? So we need, let's say, to find alternatives. The main problem, and actually this is where I have placed here this sad and happy face, you know, because it's like you go into a bakery and you discover you just find their bread. Okay? So these are the cakes. This is the bread. Okay, we could say like this if you look in terms of energy density. Fossil fuels are very attractive because the energy density is very high. When you look to hydrogen, in terms of volumetric hydrogen, in terms of volumetric energy density or into batteries, the fossil fuels are, let's say, winning. So the alternatives that are nowadays, let's say, being proposed, so besides hydrogen, we have methanol and ammonia. So we are going to explore a bit these issues. But before, don't forget that we are on transition. 80% of the energy in the world is still based on fossil fuels. So let's look into the CO2 problem. When you burn 1 ton of carbon, you emit almost 4 tons of CO2. And in Europe nowadays, companies pay 80 euros per ton of CO2, which means that almost 300 euros per ton of carbon. So if you have a system running with coal, you pay more for the tax, carbon tax, than for the fuel. Okay? So then we need to look into this situation, how much carbon you are emitting, and companies are facing a very, very difficult situation at the moment. So, although, for example, wood or biomass emits a lot of carbon, it is from sustainable origin. And then, okay, methanol, hydrogen, ammonia, so these two fuels don't emit carbon. Methanol emits, but maybe if it's from a sustainable origin, there is not a big problem. Okay? So, be careful when you start to see, let's say, this type of strategies that nowadays are very fashioned, that is carbon capture and utilization. Sometimes they say, we capture CO2, you use it to produce liquid fuels like methanol. This methanol is not from renewable origin, so also is not the solution. So in the end, the carbon taxation here is the economical driving force for all of this. So for example, from the point of view of technology, if for example, we were used to have burners that burn the fuel with air, and you reach, okay, almost 2000 Celsius, this is without heat losses. If you have a system for carbon capture, you need to change the strategy. Why? When you burn air with the fuel, you have CO2, you have water, and you have the nitrogen from the air that you get it in the exhaust. The water is very easy to separate from the CO2. You just decrease the temperature, you get condensation of the water. But it's difficult for you to separate the CO2 from nitrogen. So, what you do, okay, let's separate the nitrogen before the combustion process, because the air is at ambient temperature, is much more easy. So then you burn the fuel with pure oxygen. And what happens? You get very large temperatures. Or you change the material of your system, high temperature material, or you can do something like you recirculate part of the products back to the burner, and this will dilute the combustion and decrease the temperature. Okay? But now it's very easy to separate the CO2 because you don't have nitrogen. You just have water and CO2, you just decrease the temperature, condensate the water, and get the CO2 for whatever utilization you want. Okay, so this is, let's say, the transition, where the capture of CO2 also plays a role. But let's look more forward, so to alternative renewable fuels. And here is where we start to get confused. So, transition to what? So you have the hydrogen economy. I think all of you have heard about the hydrogen economy. You just need water, renewable electricity, produce the hydrogen. And then there is also the ammonia economy. What do? Take the hydrogen that you produce with nitrogen from air, is available everywhere, and with some, let's say, chemical process, produce ammonia. Or methanol. You do the same, take the hydrogen, green hydrogen, and get some carbon source, but sustainable carbon source. For example, from biomass, and produce methanol. Or then just use the biomass. So you have the biomass economy, which is very curious. That was the first economy that we had in the world. Before the fossil fuels, everyone was using biomass. It was the main source. And the question is why we stopped and now we want to return back to the origins. The main problem is the energy density. Okay? And also you run out of trees. If you have this type of economy, it was what happened in England, actually, in the Industrial Revolution. Okay, so the picture, more or less, is here, what was in the previous slide. So you have renewable electricity, you can produce hydrogen, with air you produce ammonia, or you can produce methanol. For example, if you get carbon from biomass, from sustainable sources, you cannot compete with the food chains and so on. And even you can still burn part of the biomass and produce renewable electricity. And with separation of nitrogen from the air and with the production of hydrogen, you also produce oxygen. So you have here, let's say, a lot of, let's say, there is a picture here where there is a lot of potential for research in different fields. Okay? And then, this is just the production. Then you have the applications. Okay? And here is where we can look into the combustion systems. So, depending on the type of fuel that you have, if you use it in the large or small scale, or stationary or non-stationary applications, which type of combustion systems can be used. So we need to look into several things, advantage and disadvantage, looking into storage and combustion properties. So, from the point of view of storage, hydrogen, as I told you, is the worst. Okay? And from the point of view of combustion, ammonia is very difficult to burn because it has very low burning velocity. And of course, methanol, here we can say is not so good. Why? Because it's a liquid. You need to vaporize it. But okay, this is the same problem that we have with diesel, and this is not really constrained. So, in the end, you need to look to the storage and combustion properties and decide, let's say, there is not an optimal solution. It really depends on the different factors. Okay? On different factors, cost, availability, and so on. So, in the end, what is happening at the moment in the world, at least from what we are facing, is that you have what is called the alternative oil field. Okay? You dig, and instead of getting oil, you produce renewable fuels, okay, with renewable electricity. But in the stream, there is hydrogen. Hydrogen is not very easy to transport because of storage problems. So I expect that local storage and utilization. So if you have a factory and you produce photovoltaic energy. You can produce locally the hydrogen and use it directly there. So for industries or residential applications. But if you want to take the energy to the other side of the world, you convert the energy into a more stable, let's say, form, and then just take it, and it is very nice if your transportation system burns its own charge. So let's say it takes the fuel and can use it. So here there are two main sectors for the maritime, let's say two main perspectives for the maritime sector. That is the boats or the ships that carry ammonia and the ones that carry methanol. Okay? So, methanol is compatible with actual internal combustion engines, and it has just a problem compared with ammonia. That is, ammonia, you get the hydrogen and you take the nitrogen from the air. To produce methanol, you need to have the carbon, and we don't have carbon everywhere available. Okay, so this is the main constraint for methanol. For ammonia, is mainly the combustion technologies and storage. Okay, it's not so easy as methanol. Okay, and then we can look, let's say, in the different sectors, and it seems that methanol, it has more potential for transportation systems, like, for example, cars that use internal combustion engines, and ammonia for large power generation systems, okay, that work under steady conditions where, although ammonia is difficult to burn, you can operate in optimal points, okay? So, from the point of view of the ship industry, so here, these two options of ammonia or methanol, this is a survey that was done in the maritime sector and the perspectives. So as you can see, the shipping companies are really looking into these two options. So there is not an optimal solution. But methanol is more expensive to produce, ammonia is more expensive to handle. So now you need to find where you have the compromise. So here, just very, very briefly, this is just to highlight that for internal combustion engines, methanol, although you can operate the engine, you have several challenges. So it has a low volatility. Why? Because it has a high latent heat of vaporization. It has a high octane number or a low cetane number. So this means it has a large ignition delay time. And the heating value is less than half of the heating value of diesel or gasoline. So this means your car should carry the double of the fuel to carry the same amount of energy. Okay, but there are here strategies for modifying the engine. So this here for methanol is not a very critical challenge, but for ammonia the problem is bigger than what we think. Because everyone heard about the CO2 cycle, the carbon cycle, but nowadays people are doing research on the nitrogen cycle, particularly in Netherlands and in Germany because of agriculture, because they use a lot of fertilizers, and this is contaminating the soil and creating an imbalance in the nitrogen cycle. From the point of view of a fuel, when you look into ammonia, you can produce what is named reactive nitrogen. Ammonia, NOx, and this one that is being very critical, the N2O. Why? Because N2O, it has a greenhouse effect that is almost, I say, around 270 times the effect of CO2. Okay, so even that you emit small amounts, you multiply this by 270, and then you decide what is better, to emit CO2 or to emit N2O. N2O is a pollutant that it depends, its production depends on the efficiency of your combustion system. So this is, besides NOx that typically is something that we look when we develop a combustion system. Nowadays, using ammonia, we also need to look into the N2O. So, if you want to develop alternative combustion technologies, I identify here two challenges. First, in short term, is the capacity for smooth transition. So, from fossil fuels to alternative fuels. So, what does it mean? It means that your burner should be fuel flexible, should burn different fuels. And after you go in the direction of having your system, combustion system, working with alternative fuels, you have some challenge in emissions. Okay? So these are basically the two things that we can look. And now I show you here some results, some of them that we have here in our combustion laboratory. So we developed there some burners to try to find fuel flexibility. Okay? So with burning natural gas, with ammonia, with hydrogen. So for example here, this is a porous medium. So it's a ceramic foam that you can use to develop radiative burners. So this is something that I identified here as a multidisciplinary topic that may have interest for people that do research in materials. And then, okay, the stabilization of the flames, and also the functionality. If you see here, you have a flame with 50% in volume, natural gas and hydrogen, and you can see the flame. When you look into a 100% hydrogen flame, the flame is almost transparent. What does it mean? Does not radiate a lot. So the radiation efficiency is low. And if you have a combustion system, let's say in an industrial furnace, where you are transferring heat by radiation, this is a problem. Okay? Okay, you can always try to look into radiative burners. But anyway, the recipe to develop a fuel flexible burner is take a look into the different strategies to control the mixing, the temperature, and of course the flame stability. That in the end depends on the mixing and on the temperature. So you have different strategies that are used nowadays: air fuel staging, exhaust gas recirculation, as I told you before, and for example aerodynamic effects with swirls, high swirl, low swirl, bluff body. In the end, control of temperature. You want to have efficient combustion and optimize the heat transfer. Pollutant emission is always important. You need to obey to the regulations. And the flame stability, it means that your burner can work with a wide range of power. I always ask this to the students of the combustion course, why at home your cooker has 4 burners. Okay? Do you cook 4 things at the same time? No, you have 4 burners because you cannot have one burner that covers the complete power range. Okay? Of course, maybe 2 to make the soup and the rice, but the power range is sometimes what limits the system. So, everything depends on system requirements. Okay? There is not a general solution. So let's look here to some examples that you get the idea. So this is Toyota hydrogen burner concept. It was a concept introduced by Toyota, I think in 2017 or 2018, where they have a typical burner where you mix the fuel with oxygen, in this case, and they were getting large emissions. So what they did, they created here a system where the oxygen is injected at a larger distance from the fuel, and they create some aerodynamic effect. So they create here a recirculation zone that somehow avoids to have a peak of temperature. So this means that in this way they could decrease the nitrogen oxides emission, because typically NOx is emitted, it comes from the nitrogen from the air, but due to the high temperatures. Okay, you have the decomposition of the nitrogen and formation of NOx. So this was, let's say, just to show you aerodynamic effects sometimes can have a big impact. So here we have the comparison of a swirl burner. You have a high swirl burner or a low swirl burner. This low swirl burner concept, it was a concept that was introduced, and nowadays many industrial systems that use natural gas burners, they are based on the low swirl burner concept. Okay? So this means that you stabilize the flame outside the burner due to some aerodynamic effects. So you have a jet with a low swirl. It creates a smooth expansion. So you always find here an equilibrium point to stabilize the flame. And you see here the person is holding the burner because this is not hot. Okay? So the flame is almost detached from the burner. You get not so high temperatures, and this means low emission. Okay? The main problem with this burner is the flame stability. If you try to do a multi-fuel burner with this concept, okay, you start to introduce hydrogen and mix it with the natural gas, you need to change the geometry of your burner. There are systems that have this, so they have variable blade angle, but okay, that is also a question of price to produce a system like this. So the alternative is to use a high swirl burner, where you create a swirl where the flame is attached to the burner. And this gives you large flame stability, but then you have problem with emissions. Okay? So what we are doing at the moment is we take a double swirl burner where we can control the amount of swirl depending on the fuel mixture. So here, instead of using a variable blade, you can just change how much air you put from the inner and outer ring. Okay? And in this way, you can, let's say, change the operation of your system in a very fast way, almost instantaneously. This is good, for example, to burn natural gas with hydrogen. Okay? And it can also burn ammonia. But then the problem is, as I told you, the emissions. So with ammonia, we need to get more careful with emissions. Why? When you have combustion of ammonia, you are introducing nitrogen from the fuel. So you produce a lot of NOx, more than if you burn with natural gas or hydrogen, for example. And this is really a critical issue besides the N2O. So then, here, the flame stability is not the only issue. So what we are looking for now is to develop a burner using the concept of stage combustion. As I told you, air-fuel staging. You can use this technique for control the combustion process. So what we do, we burn rich, so this means with excess of fuel. We don't provide enough oxygen, so this works a bit as a cracking, so you break the fuel molecule, burning a bit, and then you inject more air and you have a lean combustion. You burn with excess of oxygen. Okay? So what happens, I don't know if you all know that if you mix a fuel and the oxidizer, for example air, depending on the proportion, if you burn stoichiometric, so this means you give the exact amount of air to burn the fuel, to complete the combustion process, you get more or less the maximum temperature. And if you burn with excess of fuel, the temperature decreases. If you burn with excess of air, the temperature decreases. So this type of concept, what it does is, the typical burners, like this one, operates with non-premixing. So you mix the fuel and the oxidizer at the moment when you have the combustion. So you get high temperatures, you get large emissions of NOx. With this type of strategy, you burn rich and immediately you burn lean. So it's named the rich, quench, lean. So you burn rich, then you inject the secondary air very fast, that you don't give time for combustion, and then the combustion is completed afterwards at lower temperatures. Okay? So we are developing a system like this where you have a two-stage. So you have the first stage of the burner, rich combustion. Here is the burner. Is a typical burner. Okay, you need to find, let's say, a stabilization strategy for the flame. This is burning ammonia with hydrogen. You cannot really see here the flame because it's covered with insulation. And then we put just here a flame on the top. Why? Because we don't have the second stage. We are still developing the second stage. But you can already see that, for example, this type of flame that you see here is a flame that is very rich. Let's say it's a hydrogen flame. Not 100% hydrogen, but it is very rich in hydrogen. And you can even do something that you can even inject more hydrogen, for example. And here, now the mixing strategy, so the combustion products that come from the first stage are mixed with hydrogen and air, or just air, and these, let's say, aerodynamic effects must be optimized to get, let's say, effective, efficient burn. So here, in this figure, I just want to show you, let's say, the very fuel flexible burner. So this is the Ferrari of the burners. And they are using very large systems. So for example, in Cecil or in Simpor, the cement producers, they have this type of burners. They burn everything. Everything. Solid, liquid, gas. The problem is they typically burn everything at the same time. If you try to put this burner working only with hydrogen or only with ammonia, it is very difficult to get efficient operation. But if you want to mix everything, coal, biomass, diesel, hydrogen, whatever, they work very well, and they have, let's say, a very complicated system of air channels. Depending on the fuel mixture, you change the system operation to control the emissions. Okay? And even that the emissions are high, this is so large system that you can pay for a post after exhaust gas after treatment. Okay? So the last message is here. Okay? So in the end, there is not really a solution. So the transition is, let's say, we'll have several options. Okay? So thank you very much for your attention.